Part 207. Again, you want to start with line 18O if you're going to be looking at the space elevator components, okay? So this is line 18Q, carbon nanotubes, Kataura, space elevator, fiber optics, light absorption, Wow Seti. So there's the alien radio signal. And quotes from Wiki, optical properties of carbon nanotubes. We're going to be using carbon nanotubes with the space elevator. Within materials science, the optical properties of carbon nanotubes refer specifically to the absorption, photoluminescence, and Raman spectroscopy of carbon nanotubes. Spectroscopic methods offer the possibility of quick and non-destructive characterization of relatively large amounts of carbon nanotubes. There's a strong demand for such characterization from the industrial point of view. Numerous parameters of the nanotube synthesis can be changed intentionally or unintentionally to alter the nanotube quality. So it shows how to do that. There's a graph there for energies. Optical absorption spectrum from dispersed single wall carbon nanotubes. The unique feature is not the efficiency, which is relatively low, but the narrow selectivity and the wavelength of emission and detection of light, and the possibility of its fine-tuning through the nanotube structure. In addition, bolometer and optoelectronic memory devices have been realized on ensembles of single-walled carbon nanotubes. Then we have the Kataura plot showing the energy there. Tube diameters. So in this Kataura plot, the energy of an electronic transition decreases as the diameter of the nanotube increases. The band structure of carbon nanotubes having certain NM indexes can be easily calculated. A theoretical graph based on this calculation was designed in 1999 by Hiromichi Kataura. To rationalize experimental findings, a Kataura plot relates the nanotube diameter and its band gap energies for all nanotubes in a diameter range. The oscillating shape of every branch of the Kataura plot reflects the intrinsic strong dependence of the SWCNT properties on the NM index rather than on its diameter. Okay? So intrinsic strong dependence on the SWCNT properties on the NM index rather than on its diameter. Now the key word is the former is a metal, but the latter is a semiconductor. My thoughts. Semiconductor mirrors plus light short wave pulses sent along the fiber optic wire, adding motion mobility to pull it upwards. And this is Hiromichi Kataura. He's the one that came up with it. There's his graph. So optical absorption in carbon nanotubes differs from absorption in conventional 3D materials by presence of sharp peaks. Instead, an absorption threshold followed by an absorption increase. Absorption nanotubes originates from electronic transitions from B2 to C2 energy. So he talks about the energies, the interactions between the nanotubes, and the spectrum. Carbon nanotubes as a black body. Talks about their absorbance, the wavelengths that you can get from them, and all sorts of stuff. February 1st, 2012, my thoughts. Two factors could contribute to strong light absorption by these structures. You need light absorption into the fiber optics that hits the mirrors, which are inside of the carbon nanotube structure, facing each other as the NASA spacecraft goes up the middle of the structure along the fiber optic wire. Two factors could contribute to a strong light absorption by these structures. A distribution of the CNT chiralities resulted in various band gaps for individual CNTs. Thus, the compound material was formed with broadband absorption, and light might be trapped in those forests due to multiple reflections. One example of a central topic of our research is communication systems with high spectral efficiency. This is a way to squeeze even more information into an optical fiber and meet the rapidly increasing demand for high-speed communication links. Another topic is cost and energy efficient solutions, which is important since optical communication is now being used for shorter distances and in consumer electronics. That's from chalmers.se. Researches communication systems with high spectral efficiency. Band structures computed using tight binding approximation. And there's things, and I'm running out of power here, so that's the end of it anyways. That's the end of this video. So there's some This demonstration calculates the plots and tight binding electronic band structure of a single walled carbon nanotube. Okay, so it talks about band structures and stuff. So that's the ideas. Again, there's some other videos. I've run out of power again. Lovely camera I bought here. So I'm going to have to recharge this for another 3 hours and start filming again tomorrow. And I'll be uploading some videos. I got quite a few. We're going from line 18B all the way up to Z. Okay, so there's that. And then the next one will be, so we've got line 18O, P, P2, Q,